Alright, hello everyone. In this video, I'm going to be explaining the Radix systems. I'm going to be talking about and including what they are, the different types of number systems like binary, octal, and hexadecimal, and then how we can convert between them. The goal is really just to understand not just how to do the conversion, but why they work. Alright, so our next slide is what is radix? So the radix is just another word for base in a number system. It tells us how many unique digits are available and what each position represents. So for example, in base 10, which is a decimal, we use digits from 0 through 9. Once we go past 9, we move into a new position, like going from 9 to 10. So the radix basically defines the structure, how numbers are built, and how place values work within it. Alright, so now we're going to be talking about the types of number systems. So there are several common number systems, each with a different base. So decimal is base 10, which uses digits 0 through 9, and is what we use every day. Binary is base 2, and only uses 0 and 1, which is important for computers. Octal is base 8, so it uses digits 0 through 7. And then hexadecimal is base 16, which uses 0 through 9, and then A through F to represent the values from 10 to 15. So each system follows the same idea, but the number of digits and how values increase depends on the base. Alright, so this slide is really just going to be going over how important the concept is within the entire presentation. So the core idea is that each digit is in a number represents a power of the base. So for example, in binary, each position represents a power of 2, like 2 to the power of 0, to the power of 1, to the power of 2, and so on. So the same idea applies to the decimal with the powers of 10, and then hexadecimal with the powers of 16. Now the table here helps visualize that relationship, so it can show you how the decimal values from 0 to 15, how it maps directly to both the binary and the hexadecimal. So for example, the decimal number 10 is 1010 in binary, and A is a hexadecimal. So this table is especially useful because it shows that 4 bits in a binary directly match one hexadecimal digit. So that's why the conversion between the binary and hexadecimal is so easy, because they basically line up perfectly throughout these groupings. Okay, so this slide is basically going to explain the general rules that you can follow when converting between the number systems. So when we're going from a smaller base to a larger base, like binary to decimal, we multiply using positional values. When going from a larger base to a smaller base, like decimal to binary, we can then divide and then subtract the remainders. And then finally, when working between binary and octal or hexadecimals, we don't always need full calculations. Instead, we can just group the digits. So groups of 3 bits map to octal, and then groups of 4 bits map to the hexadecimal, so these rules help simplify the conversions and make the process more systematic. Alright, so for this one, we're just going from decimal to binary, so we switch methods and use division. Since binary is base 2, we repeatedly divide by 2 and track the remainders, so 25 divided by 2 gives 12 and then remainder 1. Then 12 gives 6 remainder 0, and then 3 remainder 0, and then 1 remainder 1, and then finally 0 remainder 1. So the important part here is that we read the remainders from the bottom to the top, because the first remainder is the least significant bit and the last one is the most significant. So that overall is going to give us 11001 to the power of, or to the subscript of 2. So on this slide, we're converting from binary to decimal. So the binary is the base 2, so then each position represents a power of 2. Starting from the right, we assign the values 2 to the power of 0, to the powers of 1, to the powers of 2, and then to the powers of 3. Then we multiply each digit by its position value. So we get 1 times 8, 1 times 4, 0 times 2, and then 1 times 1. Then we just add everything together, which gives us 13. And so the reason this works is because the binary numbers are built as sums of the power of 2, so we're just expanding it into decimal form. So here we're converting decimal to octal, which is base 8, so we follow the same division idea, but divide by 8 instead. We take 83 divided by 8, which gives 10, remainder 3. Then we do 10 divided by 8, which gives us a 1 and a remainder 2. And then finally, 1 divided by 8 gives us 0 with a remainder of 1. And just like before, we read from the bottom to the top to get the final answer, which is going to be 123. And this works because we're breaking the number into groups of 8 instead of groups by 2. Alright, so for this conversion, we go from octal back to decimal using multiplication. Since octal is base 8, each position represents a power of 8, so we take 4 times 8 to get 32, and then 7 times 1 to get 7. Then we add them together to get 39. So this works because all the number systems are based on positional values, so we're just expanding the number back into base 10. Alright, and that's all for now. I hope you enjoyed. Thanks for watching, and please feel free to like, comment, share, and subscribe. And the next video will be covering more practice examples that can give you more insight into the radix systems. Thank you.